You open up ChatGPT, you type in your prompt, you hit enter, and in a fraction of a second, an answer appears on your screen. But what actually just happened? That response didn't come from the cloud. It didn't float down from the internet. It came from a very real, very physical place. Massive buildings filled with some of the most power-hungry machines ever built by humans. Warehouses so large they draw as much electricity as entire cities. Facilities so expensive they're reshaping power grids, water systems, and even local economies. And most people have no idea they exist. Today, I'm going to show you what's really happening behind every AI prompt, what data centers are, how they work, and why they've become the backbone of the AI revolution. And quick pause. If you enjoy videos that break down how modern technology actually works, consider liking the video and subscribing. It really helps the channel, and there's a lot more coming. Alright, let's start by busting the biggest myth of all, the cloud. When people say something runs in the cloud, they're really talking about data centers. A data center is a physical building designed to store, process, and move massive amounts of data. Think of it as a factory for computation. Instead of assembly lines, you have servers. Instead of workers, you have chips performing trillions of calculations every second. Some chips handle general computing, others are optimized for AI. But the goal is always the same: keep everything running non-stop and never go offline. The cloud isn't abstract, it's physical infrastructure. Inside a modern data center, everything is built for scale and reliability. Rows of metal racks hold servers packed with CPUs, GPUs, memory, and storage. High-speed network switches connect thousands of machines so they can work together instantly. Under the floors and above the ceilings are power cables, fiber lines, and cooling systems. Battery rooms and backup power keep everything running if the grid fails. Security is extreme. Controlled access, cameras everywhere, and locked racks. It's like a personal computer, scaled up thousands of times and designed to never turn off. For most of their history, data centers powered predictable workloads like websites, email, and video streaming. That changed in late 2022, when generative AI reached the public. Suddenly, data centers were running massive neural networks in real time, answering questions, generating images, and serving millions of users at once. AI workloads are far more demanding than traditional computing. They require specialized chips, much more power, and denser hardware. Almost overnight, steady infrastructure growth turned into a full-scale race to build AI-ready data center. At its core, modern AI runs on simple math repeated at an enormous scale. Models perform matrix multiplication trillions of times across billions of parameters. GPUs are built to handle this efficiently, but they also consume far more power than traditional CPUs. A single AI image generation can use as much electricity as charging a phone, and an AI query uses several times more energy than a normal web search. When you multiply that by billions of prompts every day, the energy demand becomes massive. Power is the biggest limiting factor for AI data centers. These facilities already consume a significant share of electricity, and that demand is growing fast. Unlike traditional usage, AI workloads are dense, constant, and concentrated in single locations, drawing enormous power around the clock. That puts real strain on local grids. This is why, when companies plan new data centers, the first question isn't cost or land. It's whether enough reliable electricity is available to keep thousands of GPUs running non-stop. Inside a data center, everything is organized into racks, metal frames that hold servers and GPUs. And in the AI era, these racks have turned into monsters. Just a few years ago, a typical rack used about 10 to 15 kilowatts of power. Today, high-end AI racks already draw 80 to 120 kilowatts. And upcoming systems are expected to push far beyond that. That's several times more electricity packed into the same physical footprint. This jump in density is what's forcing the entire industry to rethink power delivery, cooling, and even the physical structure of data center buildings. All that electricity turns into heat, and if that heat isn't removed fast enough, the chips simply shut down. Traditional data centers relied mostly on air cooling, pushing cold air through server rooms and venting hot air out. But with AI racks pulling so much power, air alone isn't enough anymore. That's why many facilities are moving to liquid cooling. Instead of cooling the room, liquid is brought directly to the chips, pulling heat away far more efficiently. The trade-off is complexity. Liquid systems are more expensive and harder to maintain, but without them, today's densest AI hardware couldn't run at all. Cooling isn't optional. It's what keeps the entire operation alive. Cooling choices have real-world consequences. Some data centers use large amounts of water to improve efficiency, while others rely on air cooling or closed-loop liquid systems that use little to no water. There's no single design. It depends heavily on location, climate, and local policy. That's why where a data center is built matters just as much as how it's built. Water availability, power sources, and community concerns all shape the final design. The best projects are transparent, use water responsibly, and try to minimize environmental impact while still supporting the massive compute demands of AI. Building a modern data center is a massive undertaking. It starts with finding land that has access to power, fiber, and the right zoning. From there come months of design, engineering, and regulatory approvals. Only then does construction begin. Even at full speed, most large data centers take well over a year to go from concept to operation. AI-focused facilities can take even longer due to their complexity and power needs. By the time the doors open, these buildings represent investments of billions of dollars, all before a single AI prompt is ever answered. Once a data center is online, it operates like a fortress. Access is tightly controlled with badges, biometric scanners, and security checkpoints. Cameras monitor every hallway, and individual racks are often locked inside cages. On the digital side, cybersecurity protections are just as extreme. These systems are designed to stay online at all costs. Downtime isn't an option. For companies running global AI systems, even a few minutes offline can have massive consequences. Data centers aren't built randomly. They tend to cluster in regions with abundant power, available land, strong network connectivity, and supportive local policies. That's why places like Northern Virginia became early hubs, and why new regions are now racing to attract investment. For local governments, data centers can be financially attractive. They generate significant tax revenue and infrastructure spending. But once construction ends, these facilities don't employ many people long term. That trade-off is something communities increasingly have to weigh carefully. Data centers are built with failure in mind. If grid power goes out, massive battery systems kick in instantly, buying time for backup generators to start. In most large facilities, those generators run on diesel and are rarely used, only during emergencies. Because of environmental concerns, operators are now testing alternatives like grid-scale batteries, gas turbines, and even hydrogen systems. The goal is simple. No matter what happens outside, the servers inside must keep running. This massive build-out is led by a small group of companies known as hyperscalers. These are companies that operate dozens, sometimes hundreds of data centers around the world. Names like Amazon, Microsoft, Google, Meta, and Oracle dominate the space, each racing to build more capacity than the others. They're not just buying servers, they're designing custom chips, building power infrastructure, and spending tens of billions of dollars per year to stay ahead. In the AI era, computing scale is a competitive advantage. There are a lot of misconceptions about data centers. They don't cause random blackouts. Power grids plan years in advance for these loads. Backup generators aren't running all day, they're there only for emergencies. And not all data centers are water guzzlers. Design choices vary widely, from air-cooled facilities to closed-loop liquid systems that use almost no water. Most of the real impact comes down to planning, transparency, and how responsibly these facilities are built. AI isn't abstract. It's not just code and algorithms. Running in the background, it's concrete, copper, silicon chips, water, and enormous amounts of electricity. Every new AI capability depends on physical infrastructure being built fast enough to support it. And that's the real challenge ahead, scaling this technology without overwhelming power grids or the communities that host it. The future of AI won't just be decided in software labs. It will be shaped by energy systems, infrastructure, and the real world. So the next time you open ChatGPT, type a prompt, and hit enter, you'll know what's really happening. Behind that instant response are massive buildings, enormous amounts of power, and some of the most complex infrastructure ever built. All working non-stop, so AI feels effortless. If you found this breakdown useful, let me know. And I'd love your input. What should we dive into next? Do you want a deeper look at GPUs, the power grid, AI chips, or something else entirely? Drop your ideas in the comments. I read them, and your suggestion might be the topic of the next video. Thanks for watching. I'll see you in the next one.